Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, Knowledge Revolutions, From Arithmetic to Industry 6.0. Humans have created two sources of knowledge that support current development and the future in which we will live: mathematics and artificial intelligence. Since their creation, these sources of knowledge have generated passive and nonviolent revolutions that are the engine of humanity. In this class, these two processes will be presented. Mathematical revolutions, from arithmetic to parallel thinking. A brief history of mathematics, focusing on the evolution of optimization applied to real-world problems. The list of short introductory lectures to decision-making artificial intelligence are presented in the picture. The origin of mathematics is the arithmetic, which begins its development with the appearance of humanity. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. The appearance of algebra is in the near to the year 800 BC. Many centuries passed since the apparition of arithmetic. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. The evolution of algebra starts from a school notation, oriented to small models, not scalable, to become a professional, industrial, and scalable algebra, oriented to the present modeling of the large systems that make up the real world. If two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming models, MP, which in essence is a collection of algebraic elements. Additionally, the entire mathematical representation of a controlled real-life system is represented by one and only one reduced-form math model, using algebraic equations to describe the system and its dynamic. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The principles of transitivity between MP models can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems, to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. For example, growing scientifically without handling algebra is a utopia. The difference created by the mastery of algebra with respect to arithmetic is an abyss, not a gap. Perhaps the second great mathematical revolution. It is the birth of the fundamental principles of optimization. Based on differential calculus. René Descartes was a French mathematician, physicist and philosopher, considered the father of the algebraic and differential geometry. Sir Isaac Newton was an English mathematician, physicist, astronomer, and theologian, widely recognized as one of the greatest and most influential scientists of all time. He was a key figure in the philosophical revolution known as the Enlightenment. Newton made seminal contributions to optics, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing infinitesimal calculus. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. The creation of the digital computer gives rise to modern mathematics, oriented to the production of algorithms that can solve complex problems in a computer. First, we must consider the Turing machine, a theoretical model of a computer created by Alan Turing in 1936, which laid the foundations of modern computing. Although it was not a physical machine, his concept proved that a simple device could run any mathematical algorithm imaginable. Alan Turing was a British mathematician, logician and computer pioneer, who lived between 1912 and 1954, whose technical brilliance was fundamental to the development of modern computing and artificial intelligence. During the Second World War, Turing led, at Bletchley Park, the team that deciphered the Enigma machine, used by Nazi Germany for its secret communications. It is estimated that his work shortened the war by at least 2 years and saved millions of lives. In 1950 he proposed the Turing test, designed to determine whether a machine can exhibit intelligent behavior indistinguishable from that of a human being. George Bernard Dantzig was an American mathematical scientist who made contributions to industrial engineering, operations research, computer science, economics, and statistics. Dantzig is known for his development of the simplex algorithm for solving linear programming problems, and for his other work with linear programming. In statistics, Dantzig solved 2 open problems in statistical theory. The primal simplex algorithm can be considered the starting point of applied mathematical programming, and the birth of computer-oriented mathematics. Mathematical programming is characterized by having an objective function as decision criteria, and a mathematical model, based on a set of constraints that represent the industrial's process, and the business rules. Since its birth, computer-oriented mathematics has evolved in speed, and in the ability to solve increasingly complex problems. The image presents the evolution of the Gurobi solver, from its first version, in 2009, to the last in 2023, this for discrete optimization problems. Those who do not learn to implement algorithms will live in a world unknown to those who do. These people will have difficulty understanding the word algorithm and trying to imagine its meaning. The most complicated thing will be that they will have serious limitations to say what they want in this new era. In a relatively short time, 25 years, mathematics oriented to parallel computing emerges. This new revolution is not pressured by parallel processing, since it did not exist. The pressure is generated by the need to speed up the solution of large problems in a digital computer. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Benders partition, or Benders decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in all real applications. The importance of Benders' theory, which followed the work of Dantzig-Wolff, is that it resulted in parallel optimization, based on the theory of duality. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex, which today is the key to a dynamic language for cognitive robots, based mathematical programming algorithms to build artificial hypothalamuses. Duality theory is the key to create a generalized language between robots, or algorithms, that represent different types of systems. Today, it is the support of parallel and distributed artificial intelligence, that is the base of artificial brains. This gives rise to artificial intelligence based on mathematical programming, or to mathematical programming based on artificial intelligence. This integration of methodologies is a fundamental aspect of the artificial brains. The growth of parallel optimization-oriented technologies has been significant over the past 2 decades. The image presents the growth of Benders' theory from its inception in 1962 to 2016. The green bars, based on a visual projection, presents the expected growth in these years, which is exponential. On the other hand, the speed increase provided by large-scale theories is significant. The table provides information on various types of problems, solved with several variations of Benders' theory. The column time ratio solver/Benders presents the relationship of solution times for different sizes of problems. The content is Benders times faster. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Benders' theory. Given the complexity of the real world, which involves mathematical models of all types, linear, nonlinear, discrete, continuous, convex, non-convex, etc., it cannot be thought that with a single methodology, all the problems that make up an artificial brain can be solved. Therefore, it is required to have access to multiple large-scale optimization methodologies, which, using the principles of cross-decomposition, connect all mathematical problems, to perform autonomous distributed optimization in real time. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. In 2004, General Algebraic Modeling Systems Incorporated, GAMS, reported experiments in the speed gained using 200 CPUs in parallel was 60 to 1 times faster, with its corresponding benefit in accuracy, if parallel processing is used to increase the quality of the results. The union of large-scale technologies with parallel computing is increasing every day. The image indicates that a complex optimization problem, which can be solved in a unit of time, say an hour, using simple sequential methodologies, could take 400 hours, 16.66 days. If the appropriate technologies are not available, an unsuspecting professional would conclude that the problem cannot be solved in a reasonable time. Again, mastering a new methodology creates one chasm, not a gap. This time the abyss can generate two different worlds in the scientific field, those who understand and live the parallelism and those who do not. The situation becomes more notorious when money begins to be essential to enter this new world. Computer power and mathematical programming. All the developments in mathematics applied to solving real-life problems converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. The image presents an exponential forecast for the growth of quantum processing power. The difference between supercomputing and computing creates a chasm, not a gap. Artificial intelligence revolutions, from arithmetic to Industry 6.0. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the article, A Logical Calculation of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to explain how the brain could produce highly complex patterns by using many basic cells that are connected. Neural networks were growing, and in practice they took the name of artificial intelligence. They were also called machine learning. Digital industrial revolutions are directly linked to the computing power of computers, and in the boom that this gave to a new form of knowledge, which ended up being artificial intelligence. Today, the evolution of industrial revolutions is conceived as Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift. We move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines and biological systems to create living, regenerative and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are: integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are: mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. In 2020 there was already an awareness that the impact of industrial revolutions could be negative, and that this is apparently still happening. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. One aspect that becomes fundamental is the lives of professional people. Although professional development normally evolves to its maximum level at the end of university. However, it is common for professionals to lose knowledge during the exercise of their work and reach low levels of useful scientific knowledge. In the example, after high knowledge developed at the university, the actual exercise is limited to Excel, which is fundamentally arithmetic. This is another barrier that must be overcome. The difference between a scientific life and a real and ordinary life generate a big chasm, not a gap. Human brains, a swarm of neurons. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based on the partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic model, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms, working autonomously and permanently, to achieve the goal proposed by the decision maker. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Not teaching young professionals the principles of parallel rationing, derived from the new mathematics, is a serious mistake. Each society that does so will end up paying its consequences, which in simple words, will lead to poverty, and a growing scientific backwardness, an abyss, which generates two different worlds that will not be compatible. RCADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.